All right. It looks like we've had quite a few questions and a little bit of back and forth already in Slack. And I'm wondering if we have Shudong Sun on
Yep.
the last and most recent. Yeah, can you?
Okay, so really impressive work. And I was just wondering, like, what causes a false positive? Can you elaborate more on that?
Yeah, so the first reason of the false positive is that it only looks at the one function. So this is somehow works because ROS programmers tries to encapsulate the unsafe code in the smallest regions. So the unsafe part contained in the small region. So it works pretty well. But Rudra misses the bug that are caused by the multiple interaction of multiple APIs. This leads to both false positives and false negatives. So this is one of the common reason. And the second reason is that our heuristic is based on the API definitions, and we have some manual models, not a systematic approach. So that's another reason for false positives. But it was a trade-off to achieve the scalability that we aim for.
Yeah, makes sense. Thank you so much. Really impressive work.
Thank you.
Let's see. Infang, Chen?
Hi, great work. So my question is that, so this work is focusing on the unsafe API encapsulated in the safe API. And you also mentioned that there is an unsafe API directly exposed to the user. So I wonder whether you have explored the other direction, or is it interesting, or does it have some challenges? Thanks.
So finding a bug in the API that is explicitly defined as unsafe is a little difficult because it is difficult to distinguish between whether if the user misused the API or the API is wrong itself. But on the other hand, if we focus on the unsafe API encapsulating the safe APIs and display the proof of concept code that shows the undefined behavior without using unsafe code, then that is unequivocally considered memory safety bugs. So the reason we focus on the second type of bug is because the first reason is that it's more serious because it allows users to cause memory safety bugs without using unsafe code. And the second reason is that it provides the objective definition of memory safety bugs, unlike the bugs in the first case.
I see. That makes sense. Thanks. I think there is another question in the Slack.
Sorry, I'm muted. I was trying to call on Bogdan. You'd think after a couple of years I would learn to unmute, but
yeah, I could see you talking, but I was a bit confused. So yeah, just a quick question. Great work, by the way, like all the works that have been presented in this session, all are great tools. I was wondering if the scalability issue is just for the intra-procedural program analysis that you use, or due to that, or does Rust poses any other, challenges for scalability reasons?
So I think the choice between the precisions and the scalability is a fundamental dilemma of all program analysis. And
right, yeah.
So still, I think there is a room to improve if we dig into that direction. But since we are finding a new bug patterns in the safe Rust, we didn't want to take too much things together at the same time, because we need to implement our own analysis based on the Rust IRs without using the LLVM IR framework, which has more mature frameworks that we can reuse. Those are the reasons that we decided to use the intra-procedural analysis in this work.
Right,
and
okay,
also,
that makes sense.
Yeah, and also another thing that I brought up earlier, because there is a previous report that Rust programmers tries to test their unsafe code more thoroughly than safe code, and they try to encapsulate unsafe code in a small region. So intra-procedural analysis we observe that only using intra-procedural analysis by using intra-procedural analysis, it is more feasible in Rust than other languages because Rust programs already try to encapsulate their unsafe code in small regions.
Oh, right. Yeah. Awesome. Yeah, that makes perfect sense. Thanks. Thanks a lot.
Next, we have a question from Fogo Tunde Onodere. Are you still with us?
Yes. Yes, I just had a small question. I wanted to kind of clarify how you narrow down the scope of analyzing, specific functions, how you narrow down those functions to perform static analysis on, and yeah, how that was.
Yeah, so that's a good question. So we first started by reviewing the known Rust security vulnerabilities known to the Rust Security Advisory. That's where we started. And as our team is also like Rust programmers, and by reviewing those bugs, we think, oh, this might be the bug that I might also make or something like that. We started from there, and we also tried to audit the famous Rust packages by ourselves and found a few bugs. And based on that, we started designing a few candidates. And these 3 bug patterns here we are presenting are the most successful candidate we have found. There are like 1 or 2 more experimental patterns that didn't make into the paper. And that's how we reach it up in these 3 bug patterns.
Okay, so just a quick follow-up. So, for example, if you're faced with just a new Rust application, do you need to kind of trace the application from maybe using some certain inputs to get to those functions, or or you kind of look at the candidates that you've kind of identified?
No, our tool is a static analyzer, so we don't need any additional input from the user. So the reason that the dynamic, so that's one of the reasons why dynamic approaches fails to find the bugs found by Rudra. So dynamic approaches require the test cases that trigger the undefined behaviors to found bugs. But what we observed is that test cases are not written to expose those memory safety bugs in the encapsulated API. So that's one of the reasons why we decided to take the approach of the static analysis instead of approaching it in dynamic way.
Okay, thanks.
All right, I think we have time for one more question from Tyler Gu. Tyler, are you still with us?
Yes, great work, Yechan. So my question is regarding the high false positive rate. Does Rudra has any way to, so I was wondering what's the experience of identifying these false positive reports, and is there any way for Rudra to provide any debugging help to the programmers?
So I think with better like analysis framework, as in LLVM-IR, ported to the Rust IR, I think that might provide a better false positive rate than the current status. And to handle some of the false positive issues, we are porting our algorithms as a lint tool called Clippy. This is the official lint tool. And some of the bug patterns have very high true positive rates. So we are manually porting those small sub patterns as a Clippy lint, and 2 of them are currently integrated to the official Rust lints right now. So that's one of the way how we are handling the false positive issue.
I see. Okay.
All right.
Thank you.
All right. So let's see, do we have any questions? We don't see any questions yet. Okay, I have a question. So that's a very interesting result. So I'm wondering, like, what is your bigger takeaway for the developers who, well, I guess a lot of developers believe that, okay, if I use a program that is in written Rust, I have a much higher trust in terms of memory safety. But you find, okay, because you use unsafe trust, there is this problem. What's your message? Do you think that is still the overall takeaway? Or in another way, for example, have you considered, I guess, just some qualitative idea, if you compare the unsafe trust code versus regular C++ code in terms of memory errors, especially memory errors that you can check, which one do you think is more buggy, more error prone?
So yeah, could you hear me well?
Yep.
Yeah, thank you for the question. So we, our team believes that Rust actually believes the practical safety over the C and C++, like the traditional programming language. So the results might seem like intimidating because we found many memory safety bugs in Rust. But one thing I'd like to highlight is that the safety standard in Rust and the safety standard in C++ are different. So for example, in C++, there is no clear distinction between the safety bugs and just normal bugs. So API designers might require the user on any invariant, for example, even though if there is a memory safety behavior, the API designer might say that, oh, you are not using our API in the correct way. That's because it causes a memory safety bug and it's your fault or something like that. But since Rust has a clear distinction between the safe and unsafe Rust, and what we are finding bugs is that maybe some safe APIs might have edge cases that cause memory safety bugs, but we still think that there is a large improvement in C++ because we have a clear definitions of the safety bugs, and we also observed that those bugs are cared by the community and promptly fixed by the maintainers.
Yeah, and I think another thing to highlight is that basically we were able to audit the entire Rust ecosystem because of the unsafe delineation. If this was C or C++, you can't run a static analysis on every single like C and C++ code out there. But in Rust, this is something that's actually achievable.
That's a good point. All right, so okay, so we see a question from Yin Ho, and before you take it away, I remind all the people who ask the questions, please first introduce yourself. Thank you.
Yeah, hello, I'm Yin Ho from NUS, a PhD student from NUS, and thanks for the great talk. And I think it would be even greater if we could reduce the percentage of the false positive rate. So I wonder if you have some potential idea to achieve like lower false positive rate for your work.
Yeah, so false positives is maybe the weakest point of our work. So admittedly, there are two major reasons for false positives. The first reason is that we really want to do the ecosystem scale analysis because we are suggesting a new bug patterns that developers might need to care, and we really want to show that these are the prevalent bugs in the entire Rust ecosystem. So we valued on the scalability more than the precision. So and the selection between the precision and the scalability is a traditional dilemma in any like program analysis work. But we think that the false positive rate can be improved as the Rust ecosystem grows. So we had to manually implement all the analysis framework by ourselves using the Rust compiler IR. But this is in comparison to the LLVM IR, like C and C++, where other like existing great analysis framework already exists, and you can reuse a lot of things made from the previous work. So I think as the Rust ecosystem grows, we will have more like reusable frameworks for this type of work. And I think such development will certainly improve the precision of the Rudra work or other like future Rust analysis works.
I see, thanks.
Great. So next, Masanori.
Hi, can you hear me?
Yes.
Okay, I'm Masanori at the University of Tokyo. Thank you for the talk. I skimmed the papers, and it seems Rudra found a few bugs in Rust-based kernels, and it found 2 bugs. And considering the number of unsafe is used in the kernels, I think it is small. So I wonder if this is because Rust-based kernels does not use complicated features such as high-order functions, or this is because the existing kernel implemented it so well. What do you think about it?
I think your high level, thank you for the question first. And I think your high level observation is correct. So the 3 bug patterns that Rudra focuses on are all related to the generic types and type parameters and the interaction between the generic type parameters and the unsafe feature of the Rust. And Rust kernels tend to not use too much generic code compared to other like generic Rust user level libraries. So that's one of the reasons why the bugs found by Rudra in kernels are slightly less than the bugs Rudra found in the user level libraries.
Yeah, thanks.
Yeah, on the other hand, we also have an interesting observation about using Rust in kernel, so that the isolation scheme, so we have observed that recently some Rust-based kernels are using Rust safety as an isolation scheme, and we also discussed some of the safety concerns in that design. So that is in our paper. So if you are interested in that direction, you might want to check that section of the paper. Thank you.
Yeah, I see. Thank you.
Oh, there's more hands. Let's see. Sishuai.
Hi, Yechan. Hi, I'm Sishuai. I showed up in the previous talk. This might be a selfish question because I like to test the kernels, but one thing I noticed is that kernel developers start to write kernel code in Rust, which means the current kernels are partially Rust, partially C language, and partially assembly. Would you think Rudra would be a system that is generic to such software that is written in different languages, including Rust?
So right now, we don't consider any cross-language boundaries, but surely it is an interesting direction that that was the future research. We also see a lot of like interaction, like using Rust to build the Python backend and expose Python API or something like that. So cross-language analysis that involves Rust is all. I think that is an interesting future research direction, but in this work we don't touch that yet.
Yeah, currently only bugs that are like purely in Rust code would be found. So if you had like a kernel driver in Rust that had a bug in it, it could find that, but nothing like cross language.
Great. Howei.
Hi, great talk. I'm Howie from NUS. So I saw that in the previous session, someone asked about integrating into Clippy. So could I ask, like, are all of the heuristics and checks that you have currently integratable into Clippy, or do you face any challenges when you are integrating them into Clippy?
So thank you for the questions. And one of the biggest architectural difference between the Clippy and our work is that our work tries to do the whole program analysis at once. So we have a like clearly defined routines, like some collections done in the first stage and the analysis is done in the second stage or something like that. And Clippy is more like a lint that focuses on the small parts of the language. You can implement a similar thing in Clippy, but it's hard to implement like the global cache that is shared by the analysis or something like that. So it's possible, but it's not straightforward. But we are still trying to port some of the sub patterns that we observed with high true positive rate to the Clippy lints. And we currently have 2 lints ported to the Clippy right now.
Cool, thank you.
Okay, great. Any more questions for the author?